So this is the continuation of going over the Euler equation and what these terms actually mean. So in the earlier video, I went over this term and the external force term, so basically the acceleration, straight acceleration term, and the external force. So the next term in this equation is this term, which is the vection term. So the question is, what does this actually imply physically? So suppose we have a stream of fluid that for some reason is bending. And zoom in on that a bit. So there's this fluid stream that's just streaming along this table. And we've got this blob. This is the notorious W blob that's moving along in the fluid. That's the one getting examined by the integral. And basically there's flow lines in the fluid, so this is the direction of the flow. And this flow is basically curving, so this blob goes along. It has its velocity along the flow lines, and it starts moving along the flow lines. And as it moves, it basically is forced to change its velocity because it has to follow the flow of the other fluid. And this change in this fluid's velocity, because it's basically moving along the velocity field and the velocity field is forcing it to change velocity, is basically what vection is. So basically the idea is start with a fluid at this time, and it's at this point in the flow lines, and then it moves to a later time and it basically changes direction. So going back to the whiteboard. So vection. So to look at vection, basically I'm going to set up this situation. I think I'll actually draw it down here. So basically here's the flow lines. And I'm going to redraw these guys in blue. Okay. So there's these flow lines that are going along. And then at some point they change direction. And this is going to be T naught. And then at some later time, flow lines should still be essentially the same. So this is at T naught. Plus a short time later, a small delta time later. And inside these flow lines, there's going to be a point. That's basically being tracked. So that point starts out somewhere there, and then at a later time, it's somewhere over here. Actually, it moved up a little. So it starts there, it moves to there. I'm also going to draw some white here because it's kind of hard to see. So this point basically moves because it's just being carried along with the current, basically. So to look at this, basically there's two terms. So first off, there's the change. Let's draw the coordinate system. So this is y, and this is x, as usual. And let's say this point starts at a location of x naught, and it moves to a new location called x1. So there's this change in y, or change in the velocity in the y direction. So the change in the uy, which is the velocity in the y direction. that basically equals the uy at x1 minus the uy at x naught. Then the change in x equals x1 minus x naught, which is going to approximately look like actually the velocity, this delta t, which is going to be just delta, which is the change in time, times the velocity x. Because it turns out that this particle is of course being carried along by whatever the fluid velocity is. That's how it's moving. So if the velocity is moving at its own rate, that's how much distance it moved in this little delta time interval. So from this, I can come up with the equation for the change in y, uy, or change in x, and this is going to equal uy x1 minus uy x naught divided by delta x. But then I can just substitute in this for delta x. So this guy now comes out to be y x1 minus uy x naught divided by what I had up here, which is delta representing the change in time, ux. And since this delta is actually making it look a little bit like that's delta of ux, what I'm actually going to do is I'm going to change the notation and actually make this a delta t. Make it a little bit cooler. So it doesn't look like it's a delta ux. So this is delta t, and then this is basically times ux. So delta t times ux. Okay, so the next thing that's useful to observe is that change in uy, change in ux, that basically goes like duy dx so what I can basically do is I can say this guy basically goes like approximately like duy dx, and then take the ux over to this side, so I have ux on this side, so ux times duy dx is basically going to go like uy x1 minus uy x0 over delta t. At this point, notice that this is basically an acceleration. So this basically looks like the change in y, uy for change of that particular particle for change in time. So this is not the change in uy. This does not equal the full vector field x vector comma t dt, because u vector in this sense is fixed to the coordinate grid. Is fixed to coordinate grid. This, however, is the acceleration of the particle itself. So what this actually looks like is basically this ux dx basically goes like it's the velocity of this particular particle at x1. Maybe I should designate this, say, let's put a k up here, so it may, why this is the velocity of the kth particle. So minus well, actually these things are actually the fixed velocity field, but because this particle is moving between these two velocities, it's undergoing an acceleration because it started out at this velocity when it was here, and then it moved into basically a higher velocity field in the y direction. So now it's at a higher velocity. So this is an acceleration of the actual particle. So this goes like an AY, but it's a special type of acceleration. It's a AY of the particle. So this is of the particle. And it's due to moving through due to the fluid flow. Change in direction. Of flow. So the particle is actually just accelerating because it's moving. So if this is written out in its complete form, it turns out that in the full form, in the more general form, there's not just this ux duy dx term. There's actually all three terms. So there's basically a term ux duy x. There's also going to be a term that's analogous, that is uy dy. And there's going to be another term which is uz z, which equals, by definition, this is basically the definition of u vector dot the gradient of the uy component. And of course the Euler equation, the full equation, is just shorthand for this being done for all three components. So this is basically shows how this type of velocity, this is basically what's going on that's actually generating that evection. Term is basically just due to these changing velocities. And in the integral form, going back, so the integral form, well, this is deriving the Leibniz. If this was uy and then there was this blob, which is a fluid, as this blob basically slides, I actually have the direction of y, I think, is actually exactly opposite to where it should be going, going in the other direction. But as this blob basically slides, what happens is it basically loses some velocity and it gains velocity. So it can be thought of as it slides over the velocity field. It's basically like eating velocity and regurgitating velocity. So if it eats faster velocity, then it keeps moving faster. And if it loses slower velocity, or vice versa. So basically, its velocity basically changes as it basically absorbs velocity with its front membrane, in a sense, but basically the outer edge of the integral. And of course, in a real velocity field, this wouldn't be a perfect cylinder, it'd start distorting. as it moved also. That is basically the explanation for the vection, and it can be seen in the program. So this is basically the animation of the blobs, and as they move along, these die blobs basically spread out and they also tone, so they're essentially getting an acceleration, and it's simply due to the flow of the fluid. So there's this vortex in the fluid with all the arrows circling around it, and these die blobs are moving along around the vortex, and they're getting pulled inwards towards the vortex as they spin around, so that they basically rotate around the vortex, and that's basically the vection. And of course there needs to be so the vection basically is a kind of it's like a kind of acceleration, essentially. It's a measure of acceleration. And of course there needs to be a force to actually cause that acceleration, and in most cases the force that actually causes the acceleration is usually pressure. So this is the pressure gradient. So the vortex actually has a lower pressure in the middle and then higher on the outside. So that pretty much brings to, that is pretty much the beginning of the next topic, which is the discussion of the pressure gradient. So the next term in this equation is the one right here. So this is the pressure. Or whether more precisely, the gradient of pressure that actually enters into the equation. So to start with, there's already two possibilities have been covered. One is the pressure could just go into the du dt term, so it basically causes the acceleration. There's supposed to be a rho there. And the other is it could be, for instance, just balanced by the external force. The external force could also just balance against the pressure. So, going over this real quick. So it could be or it could whether not balance, but it could actually just lead to acceleration. Turn into acceleration. Into acceleration. So that's basically the rho du t case that I was gone over in the beginning of these videos. So that basically goes like negative gradient of p. So it could turn into acceleration. It could also be balanced by pressure. Well, that is, it could be balanced by an external force. By external force. So that's basically this equation. Rho g equals the negative gradient of pressure. Or actually equals the gradient of pressure. Okay, but there's other cases, and one question is, where does pressure actually come from? So to start with, start with a case, actually just assume pressure did not exist. So we'll check. Let's examine the case where pressure actually didn't exist. Pressure equals 0. So there is no pressure, there is no gradient of heat. So the question is, what does this actually looks like? So to begin with, incompressibility actually ends up being maximally violated in this case. So what happens is gradient dot u vector does not equal 0. So basically, this is the case. There's a bunch of these little fluid blobs, and they're all moving around with different velocities, so they're going in different directions. And just assume in this case, back to the whiteboard thing, let's also assume, make some other assumptions. Let's also assume the external force is 0. So let's also go G vector equals 0. So for that, the only remaining part of the equation that exists for the normal Euler equation will look like this. So it would have the omega t and then it would have d by dt. In this case, rho is going back inside the equation because density is no longer guaranteed to be constant. And it has a u vector, and then there's the rho, except that's not a gradient there. No, that's not a u, just a gradient. And then there's the rho vector, or the rho variable, and then the u vector. Rho is still a scalar, but it depends now on time and space. So in the normal Euler equation, this would equal 0. Question, what does that actually equal? So these are the only terms remaining in the Euler equation. So basically, there's no pressure, there's no external force, so there's just the velocity term and the advection term. And there's all these little blobs going wherever they want to go. So what they basically do is they undergo advection, which means they slide off in different directions. And what actually happens is they actually start to overlap. They actually collide, they run into each other, they pass through each other, they leave big voids where there's low density, and they bunch up in areas where there's much higher density. So basically what happens here is without anything to stop these blobs, there's no external force, there's no pressure, there's just the change in the velocity and the advection. What the advection does is it basically creates this velocity field that really maximally violates compressibility, because everything is basically sliding through everything else. So in this scenario, instead of this side being equal to 0, what this side actually equals to is the full equation, which basically equals this interval, which is negative rho vector And then there's the gradient dot u term, that in this case does not disappear, and dv. So there's these serious changes in basically the compression as well as the density of the fluid right here. So basically what's actually going on in pressure is actually necessary to stop in order to go ahead and fix this term, because if this pressure does not exist, then this term pretty much has to exist to balance the equation. This side of the equation cannot in general be equal to 0. So if this side of the equation is 0, this side of the equation generally is not going to equal 0, so that's not going to work. So the only way to set pressure equal to 0 is basically to reintroduce the gradient dot u vector term. So the real equation involves pressure. So question in incompressible fluid equals gradient of P. Well, actually this is an interval. dV. And gradient of P must be non-zero. At least if there's any changes in velocity, as well as for any like varying, basically Covey U vector field. So basically things are moving around a Covey. Pretty much gradient of P is what basically restores the fluid into a fluid. If you don't have that and there's just varying velocities, what's going to happen is it's going to bunch up and spread out and do other strange things. Okay, so a good case for pressure versus advection is actually the vortex. So here's a vortex. Well, basically this fluid is running round and round in a circle inside of this field. And since it's going around in a circle, of course, at a given point it has a velocity going in that direction. And if nothing else was trying to stop it, advection would just make it go farther and farther off in that direction, because it's basically any point here is going to just travel along a straight line on its own. That would be what advection would do. So in order to actually have the advection term, for the advection term to actually work, because the advection term actually has it change direction, that implies acceleration. So the advection term is actually calculated because it actually changes direction it goes. There's actually going to have to be this inward acceleration, which is going to come out of the advection term. And for this acceleration to exist, and in this case, this vortex does move slowly, but it almost stays in the same spot. So in this particular case, the du dt is almost 0. So basically in this case that I'm looking at, is I'm pretty much just looking at the advection versus the pressure. So this case is basically going to write out this formula. It's basically just the advection term versus the pressure term. So there's basically the advection term, which is u vector dot gradient u vector. And this is basically just going to equal, it's going to approximately equal a negative gradient of P. Except there's also a rho in there. So this term is effectively acceleration caused by basically this arcing flow that's basically an arc around. And this goes like, this is basically the mass. And this is going to be the force that basically balances everything out. So going back to the image sequence. So basically there's this flow with the vortex. So each particle in the flow, if it was left to its own devices, would just keep accelerating outward. Because of evection, evection actually implies that the particle moves around in the circle, which means there's basically acceleration that needs to exist to cause the proper evection. And this acceleration, of course, requires a force. So this is just looking at the pressure gradient. So the pressure in blue in the middle is the lowest pressure, red is the highest. So going out of the vortex, there's basically a low to high pressure zone. So this is the gradient of pressure. And the gradient of pressure creates a force in the opposite direction. And this force, which is caused by the gradient of pressure, is basically what causes the evection. So this is basically, the one side is basically the force inwards, and the other side is basically the acceleration times the mass, which is basically acceleration basically mass times acceleration caused by the evection, and then the other side is the force, and it just balances out perfectly. And so another example of this is a pipe, and assume this pipe basically has steady state flow, so it's been, whatever's in the pipe has been flowing long enough that it's no longer, the velocity field inside the pipe is no longer changing. And there's this water kind of mixed with maybe steam that's flowing inside the pipe. So there's basically flow lines inside the pipe. Water's following these flow lines coming from this direction and flowing in that direction. And there's the velocity. It has higher velocities here and lower velocity there on the inner kernel. And if it was just if it just went with evection and there was no force on this whatsoever, of course it just deviate and go out through the outside of the pipe. So there has to be some sort of force to actually cause the evection. And that force is actually the pressure. So what actually happens in this pipe is it actually builds up a pressure gradient. So there's actually higher pressure here and lower pressure on the inside. And this pressure gradient that goes from the low to the higher pressure basically creates a force in the other direction. And this is what basically keeps the fluid flowing around like it's supposed to be around the curve of the pipe. And this image, by the way, was OpenAI interpretation of an ANSYS image, actually. That's available on the internet. So that's basically the principle of how pressure basically turns a fluid back into a fluid. And that's going to come up later with the numerical simulation. So the next topic will be essentially going to the point of actually turning the Euler equation into the Navier Stokes equation, which is adding viscosity.